In this tutorial, we'll talk about rhythm chains. So this is actually getting into the realm of true algorithmic composition, where we generate algorithmically two voices of counterpoint and produce both a rhythm sequence palette and a rhythm sequence map. So we're going to look at how it does this, the generation of the two-voice rhythm sequence palette and the rhythm sequence map, as well as the make rhythm chain function and some of its options. We're going to look at how to add a voice if you want more than two-part counterpoint. And we'll also consider some helpful post-generation methods. Consolidate notes, consolidate rests max, map over bars, tie over rests, and handle ties. Rhythm chains generate two-voice rhythm sequence palettes and rhythm sequence maps. We generate these two voices of counterpoint from user-specified rhythmic fragments. For instance, we need shorter one-beat fragments and longer 2- and 3-beat fragments to act as counterpoint. We can also control the automatic insertion of rests based on algorithmic patterns and what I call sticking rhythms, which are also based on patterns. So let's look at the make rhythm chain function first of all. As I've mentioned, this produces both a rhythm sequence palette and a rhythm sequence map. So you can access the palette just by calling the palette accessor function. Now you must specify at least 4 of each of the 1-beat and 2- and 3-beat rhythms that we're going to use to chain together to create our rhythmic sequences. And in order to work properly, the rhythms can't overlap beats, even the slower moving rhythms. So you shouldn't express, say, a half note if you're working in 4/4 as a half note, rather it should be 2 tied quarter notes. There are 17 optional keyword arguments to make rhythm chain. You can control with these things like, as mentioned, the automatic rest insertion, the activity level, which controls how many notes are going to be playing from very sparse to very active, and also these automatic sticking rhythms, which create an algorithmic insertion of some kind of repetition of, say, an 8th note or a triplet. You don't have to have those at all if you don't want to, but they can be musically useful. So let's look at a simple rhythm chain example here. We're going to specify the number of beats to generate, which will control the length of the piece. And we're going to specify the source rhythm fragments, the player IDs, and the map ID. Because we are generating rhythm sequences purely algorithmically here, it's very difficult to specify the pitch sequence palettes, the pitch curves that go with a rhythm sequence. So we have to create them algorithmically. So we're going to use the create PSPs function to do this for us. The first argument to make rhythm chain is the ID for the object itself, nothing particularly important. The second argument is the number of beats that we're going to generate. Not the number of rhythm sequences, but the number of beats. The next argument is the guts of the data, the actual rhythm data that we're going to use to create our rhythm chains. We need a total of 4 rhythms in each of the 1-beat and the 2- and 3-beat data sets in order for the algorithm to work. More would probably be desirable. We've got 4 here. So let's take a look at them. You see, first of all, 4 1-beat groups of rhythms. What we do is make a transition from the first group to the second group. What comes next is the slower moving counterpoint, the 2- and the 3-beat rhythmic ideas. There's no reason why it has to be slower moving counterpoint. This could be made up of the same kinds of rhythms or even faster rhythms than we have in the 1-beat rhythms. But the concept when I developed the algorithm was to have slower moving counterpoint here. So first of all, we have the 2/4 bars. And you can see these are all very simple duple rhythms as well. But we transition to triplet-based rhythms, as you can see here. You'll also notice that we have triplet rhythms tied over the beat. So rather than expressing here 3 triplet quarter notes, we express it in tied 8th notes so that we can have rhythms that can be split up into beats, because that's a requirement of the algorithm. So let's just look at the 3/4 bars. You can see again, like the 1-beat rhythms and the 2/4 2-beat rhythms, that we're moving from essentially duple rhythms to ternary rhythms. The last argument to the make rhythm chain function that we use here is the player's argument, and this just names the voices that we're going to create, and we're using FL and CL for flute and clarinet here. After we've created our rhythm chain object, we then need to create our pitch sequence palettes, and as we mentioned, we do this algorithmically by calling the create PSPs function with an argument being the palette of the rhythm chain object which we just created. So then we have a very simple mini function which has these two voices, the flute and the clarinet, a simple set palette of one set, and a set map which is algorithmically generated by calling the ML function, which makes a list, and we want to make a list of ones using the num rhythm sequences slot, how many sequences were generated from the rhythm chain object. The rhythm sequence palette for our slippery chicken object is the palette slot of our generated rhythm chain, and the rhythm sequence map is, of course, the rhythm chain object itself. Now you can see the piece that's generated and hear the results. If you want to create pieces with more than two voices, you can use the add voice method to add a new voice to an existing rhythm chain object. And this will use existing rhythm sequences to make a new voice. So first of all, our add voice will collect bars into groups of the same meter in the order in which they occur, so that we can then choose from the right metrical structure, bar structure, in order to add voices. So it won't be that they're playing in rhythmic unison, just in what we might call metrical unison. So the arguments to the add voice method are the rhythm chain object we've already just created, with the two voices already inside it, the player ID of the source voice, and then the player ID for the new voice. So the player ID of the source voice is either the 1 beat, the faster moving counterpoint, or the 2 and 3 beat, the slow moving counterpoint voice. And if you look at our call here to the add voice method, the example call, you'll see that we have to say 1CL as a list, because the rhythm chain algorithm generates a complete section for a piece, and you can specify the section ID if you like. So you can put it in combination with other rhythm chains with different sections perhaps. And the default, which we've not changed up to now, is to name that section 1. So we're getting the clarinet out of section 1, and we're going to create a new voice based on its rhythm sequences, matching the metrical structure so that they can be contrapuntally combined with the oboe, the new voice. So let's look at our example now using add voice to create a third voice in our piece. The rhythm chain object is essentially no different, just a little bit shorter than our previous example. And we create the same two voices, flute and clarinet. The call to add voice is exactly the way we just described it. We're adding the oboe voice. And we're also creating our pitch sequence palettes as before, algorithmically. Then we've got our make slippery chicken call. And again, it's similar to before, but now we've got the added voice, the oboe. We've got some set limits, high and low, which we've talked about in other tutorials. And we've also got our one set palette. The set map is also as before. We create just a list, which is going to create a a series of ones to match the number of generated rhythm sequences in the rhythm chain. And we've got our rhythm seq palette, which is of course the palette that's inside the rhythm chain. And our rhythm sequence map is the rhythm chain object itself. So the difference to the previous example comes here. The first thing we see is that we've got a tie over rests function. This is a post-generation function that can be useful sometimes if you want to create longer held notes from shorter notes. And this takes the slippery chicken object as its first argument, the bar number and the note number that we're going to start at, and the player. It will then tie over all of the rests that follow from that note. In order for that then to be reflected in the generated MIDI file, we also have to call the handle ties method. And we call this separately rather than implicitly in the previous method because you might want to call tie over rests many times and just handle ties once after you've done all of those calls. We also then call the rebar method, which I think we've seen before in other tutorials, just to make the shorter generated bars from the rhythm chain into longer, more manageable, more easily readable, perhaps, bars, aiming for a minimum time signature of 4/4. We then see another couple of new functions or methods for post-generation data editing. We have a sort of overriding function for slippery chicken called map over bars, which allows you to apply a function over several bars of the piece. So we're going to call map over bars over the whole piece for all of the players using consolidate notes to bring all of the ties into rhythms that are more easily read. We're also going to map over the bars and consolidate any rests into longer rests.